So now we have our last video on the order of our reactions. Much like 0 in first order, we're going to be doing several steps here where we find the integrated rate law, we find the half-life, we find the linear graph, and we find what just the normal graph looks like. So if we look at our rate first, we have rate equals K concentration of A squared. Now, much like before, let's just give you the integrated rate law since we don't really do calculus in this class. And again, if you have had some calculus, I do want you to kind of look at this a little bit and see if you can see where some of these values are coming from, even if you might not be able to replicate it yourself. So our integrated rate law for this one looks a little bit different. And if you know a little bit of calculus, that makes sense because we have A squared, not just A. So here we have 1 over AT equals KT plus 1 over A naught. Now, if you look at just the graph of time versus concentration, the first graph on this slide, you'll see that that actually looks very, very close to a natural logarithm graph. It's not. The inverse graph is not the same thing as the natural log graph, even if it looks like a little bit to the naked eye. And you might say, okay, well, how would I know that? Once you graph it, you can ask Excel to effectively tell you this. And you would know for sure by trying to make a linear graph out of it, which is what I've done in the second graph here. So in the second graph, I have T is equal to 1 over AT. So 1 over AT gives us a linear graph. Much like in the first order reaction, T versus natural log gave us a linear graph. So if you were doing this and you didn't know what kind of reaction you had, you could use these graphs to tell you that. Because you could make a graph that's T is related to natural log and see if that's linear. Or you could make a graph of T is related to 1 over AT and see if that's linear. And that would tell you what the rate is. We're not going to do that here because we're not going to make the large sets of data. But if you take a lab course, you'll probably end up doing this. So we have our rate law, we have our integrated rate law, and last thing, our half-life equation. Now, just like with the other ones, you should be able to go from your integrated rate law to your half-life equation. However, in this case, I'm just going to give it to you rather than rederive it. So our half-life here is 1 over K A naught. So again, we get that from finding that AT, our time at concentration T for our half-life, is equal to 1/2 of our initial concentration. If you fill that in and solve, this is what you'll get. And I want you to practice that on your own and just ask for help if you need it. So I'm not going to do any problem solving for this video because it is identical to the problem solving that you do for the first order reactions. The only difference is that you're using a different set of half-life equations and a different set of integrated rate law equations. But the only way to get better at those is to do it yourself. And so if you want to look for some examples, you can go ahead and check out the book for some. But really, you should just start in on the examples using these new equations. Everything else is the same, just manipulating integrated rate law, half-life equation to get your answer.